All right, so last Friday we talked about acids and bases, and we said that some acids are really, really strong. I mean, a splash of them on you will give you an instant chemical burn, and then other ones are rather weak. And we said that strong acids are defined by the extent to which they dissociate. A strong acid is typically thought of to be an acid that dissociates into 100% ions. So in the case of HCl and water, we created only the hydronium cation and only chloride anion. Nothing else remained in solution after this. Where we said weak acids do not completely dissociate, and so what you end up with is something called an equilibrium, where you've got some of your product side and some of your starting material side in solution. So all four pieces are in solution, and weak acids generally produce very few ions in solution. So the way we show this is with the equilibrium arrows. That's the thing I circled in green. Where up here we had a one-way reaction arrow, which means it goes 100% to product side. The other thing that people get confused on is that acid strength is not necessarily related to its concentration. It has to do with the extent of ionization, not concentration. All right, so what we're going to start with today is something called neutralization. In neutralization, we've actually already seen a bit in our lab with the carbonates, but it's when you combine an acid and a base together. Does anybody remember what we created when we mixed an acid and a base? We made CO2. That was one thing. What was the other thing we made? We had to put it in the oven to get rid of it. Water. So you produce water. And a salt. And if you remember, a salt is any generic ionic compound. So in lab, you made sodium chloride, calcium chloride, things like that as your neutralization byproducts. So let's take a look at some examples, and we'll do some easy ones at first. So let's say we have NaOH plus HCl. If we combine these together, we're going to get water because it's a neutralization reaction. Which one's going to be our acid, the HCl or NaOH? HCl, so this is going to be our acid. This is going to be our base. We're always going to produce water. And we have to produce a salt as well. All right, so now the question is, what's the salt going to be? Yeah, sodium chloride, that's what's left over. So NaCl. If we look at this, is it balanced? Looks to me like it is, right? Another way of thinking about this is you can break it down into a visual picture. And you can say, all right, Na plus, and then hydroxides over here as OH minus. In fact, I'm going to show this with its covalent bond. And then I'm going to do HCl in red. And during this reaction, we're going to combine each of these pieces to make water. But now you're going to form a new bond to this red proton. Looks like that. And then your leftover piece is going to be the sodium, which is positive, and then your chlorine that is negative. So sometimes people like visualizing that hydroxide combining with an acidic proton. Make sense? Let's try another one. So for this next one, I want to see if you can figure this out with your neighbor, but make sure that your equation is completely balanced. We've got CaOH2. Let's do the name for this. And then we've got HCl as well. And then let's predict what products we'll get out of this reaction. So I'll give you a minute to work on this, but check your naming and check your products to see if they match your neighbors. So let's do the easy ones first, and then I'll give you a little bit more time. Let's do the naming of CaOH2. What would that be called? Calcium hydroxide. Because it's ionic, you don't need the mono, di, tri, tetra. And then over here, we've got hydrochloric acid. Whoop. And so we've got an acid and a base. The first thing we're obviously going to make must be our water. So I'm going to put water in here. I'll put a coefficient in front of it because we don't know how many water molecules we'll make. And then what do you think the salt will be? Calcium chloride. So what a lot of students do is they say, well, we've got calcium and we've got chlorine left over. Is that right? Is that the correct salt that we should be making? Just CaCl? You need it too, right? So if we break this apart, let's do the visual representation, and it will hopefully make more sense. Calcium, we know, has a 2 positive charge. We've got 2 hydroxides floating around to bounce out that 2 positive charge, right? And each hydroxide has a -1. That means we have HCl. And just like we did before, we can circle this and we can say that makes one of the waters. But we need a second hydrochloric acid to neutralize the second hydroxide. So let's mix this together. And when we visualize this using our picture, we're going to have 2 waters plus CaCl2. So it's really important that you remember the 2. And when we bounce this 2, you can see over on the starting material side, we needed 2 of our hydrochloric acids. So plug that in. We only needed 1 of the calcium hydroxides. We produced 2 water molecules because we had to neutralize both of the hydroxide anions with 2 equivalents of hydrochloric acid. And we get 1 equivalent of calcium chloride out. Whoops. Does that make sense? Some students really like seeing the visualization and circling them. So if that works for you, go ahead and do that. If you feel comfortable doing it another way, you're welcome to do that as well. Any questions so far with neutralization? All right. So now we get to talk a little bit about environmental chemistry, but I'll try not to be on my soapbox for too long. We're going to talk about reactions of metals and non-metal oxides. So the first one is reaction with non-metal oxides. So specifically reaction of water with non-metal oxides. And anytime you react a non-metal oxide with water, you create an acid. So I'll show you a couple prime examples in environmental chemistry. The first one is CO2, that's carbon dioxide. If you mix carbon dioxide with water, what you're going to end up creating is H2CO3. This is carbonic acid. How many of you have had seltzer water or carbonated water? I'm assuming just about everybody. So carbonated water, if you taste it, has that almost, I don't know, it's a hard to describe taste to it. It almost tastes a little bit bitter, right? And that actually has to do with the CO2 they use to carbonate the water. It makes the water slightly acidic. So if you took that sparkling water out at home and you dipped pH paper on it, you'd see pretty quickly that it was acidic. This is a big problem, though, in the environmental community because we're producing a lot of CO2. We're pumping it out into the atmosphere. That CO2 is actually getting absorbed into our lakes, rivers, and oceans and making our freshwater and saltwater waterways more acidic. And I've got a video to show you more about that later. But it's a huge environmental concern. One of my big pet peeves as a chemist is people talk about climate change a lot on the news, but you don't hear ocean acidification talked about very often when that's going to be an immediate concern in our near future in the Puget Sound region.
That's what's ruining reefs.
It's ruining the reefs, it's ruining our oyster beds, it's causing a lot of problems in terms of the ecology of our ocean ecosystems.
Is there a way to counteract that? Water.
That's a good question. So a lot of people say, well, can we just remove the acid from the ocean? On a scale that large, it will take millennia to adjust. And we've changed our oceans way too rapidly. Sorry, this is a random talk, but I went to a talk a few years ago from a NOAA scientist, so an ocean researcher, and he was saying within the next 50 years, all of the coral reefs in the world will be dead. And that's even if we stop producing CO2 today. This is a very, very serious problem. All right, we'll see.
So there's nothing that we can do.
Yeah, unfortunately, the way the carbon cycle works in the ocean is it will take thousands of years for it to change. And I'll show you some examples of why I think it's a really serious problem that needs to be talked about more. The other problem that's common but is actually being managed fairly well is sulfur dioxide being pumped out into our atmosphere. So sulfur dioxide is produced when you burn coal. And when you burn coal, the sulfur dioxide will mix with water in the atmosphere. And it will make H2SO3. This is sulfuric acid. Oh, sorry, that should be SO3. Sulfuric acid. And this sulfuric acid will keep on reacting in our atmosphere to make H2SO4. This is sulfuric acid. Sulfuric acid is a very, very, very strong acid. It's one of the gold standards of strong acids. And if you have ever been to places like West Virginia, you might notice on the hillsides big swaths of dead trees. So here's a picture got there. You can typically find these downwind of the coal-burning power plants. They have gotten better at minimizing this SO2 emissions coming out of the smokestacks by installing big scrubbers on them. However, even by removing the SO2, they still are producing a ton of CO2, and there's not a good way of capturing that CO2 off of the coal-burning plants. So acid rain has been managed a little bit. It's at least under control now. In the 60s and 70s, it was a huge problem, though, before they installed those scrubbers. So in either case, though, when you look up at each of these, you see how both of these are non-metal oxides. They contain a non-metal and oxygen. Anytime you combine those with water, you tend to produce an acid. All right, I've got a little video that I wanted to show you too from, I think it's Oregon State. So let me turn on the volume here.
We have an incredibly productive ocean. When we go out there and do our research, when I'm waiting for instrument to come up, I can see salmon jumping, that's amazing.
This issue of ocean acidification, it threatens that ability to rely commercially on these resources and also to rely on them recreationally, socially, and culturally.
About 25 to 30% of the CO2 that's released from fossil fuel combustion ends up in the ocean. That lowers pH, and it also changes something we call saturation state, which is the corrosivity of that water.
Based on the chemistry of the water and how marine life respond to chemistry, the kinds of organisms that we think are most vulnerable are the ones that build the shell. So oyster shells, clam shells, and corals.
I think the things that are most important to the public to understand is that what this issue is threatening are some of our food supply. There are people's livelihoods and generations of watermen who rely on producing oysters and other shellfish. So when we talk about ocean acidification, what we're talking about is a change in the carbonate chemistry of the ocean due to the increase in atmospheric CO2 from fossil fuel combustion, as well as other local processes that change that chemistry. And so the issue comes in is that we're changing that chemistry faster than we have in the last million years in Earth's history. And that's having predictable consequences on chemistry as well as consequences on the organisms that we're we're just starting to understand now.
So we've identified the Oregon coast as one of these early impact systems. So our chemistry is already changing, and it's changed dramatically.
The waters that reach Oregon's coast, if you stand on the coast and look out and see this great blue expanse, you think, oh, that's just one big bathtub of water. I'm not quite sure what's there, where it's coming from. But over the years, we understand very well how that water gets there. And that water reaches Oregon shore from far across the North Pacific, off to the northeast of Japan, actually. When it's at the atmosphere, it gets the oxygen and the CO2 from the atmosphere mixed into it.
Oh, no. Oh. I was getting to the good part. Let's try that again. I don't know why it crashed. Oh, man. We'll try it one more time. See if I can get it back up. Come on.
The big corporate machine.
The hatchery where they produced.
Oh. I'm trying to remember where we were at. There we go. I think that's about right.
From far across the North Pacific, off to the northeast of Japan, actually. When it's at the atmosphere, it gets the oxygen and the CO2 from the atmosphere mixed into it. It's cold enough there that the water gets dense or heavy and it sinks down to beneath the waves to about a couple hundred meters and starts this long journey across the North Pacific. And there are actually two branches. One of them comes across the northern Gulf of Alaska. Another one takes this amazingly convoluted route. Along that path, the oxygen gets lower, the CO2 goes up, the pH goes down, it gets more acidic before it reaches Oregon shores. So if you think about the rising CO2 levels in the atmosphere, the water we're seeing at depth off Oregon has the signature of many decades ago.
Even if we absolutely stop the CO2 emissions today and we cap the atmospheric levels, there's still a 30 to 50 year increase we're going to see before that carbon, at least along our coast, works its way out.
The effects that we're seeing, the changes that we're seeing in the chemistry of the ocean that affects everything there, all living things and non-living things also, are changing it in ways that are going to adversely affect the things that people care about, because it's affecting the creatures that live there and their habitat.
The oyster industry in the Pacific Northwest has already seen significant losses in production in oyster hatcheries. And so what it's meant to the oyster industry is approximated about $110 million in production losses. OSU has really sort of been a leader on this topic, and it's a bit out of necessity. And so the oyster industry really contacted Burke Hales and myself to understand what was happening in these oyster hatcheries and try to explore what's driving these problems. And so because this upwelling system starts with a CO2 level that are higher to begin with and puts us closer to those thresholds for the organisms, they've had to deal with these problems kind of right off the bat. And so we've had this really productive industry academic partnership that has allowed us both to sort of provide information and applied research to let the industry increase production and deal with some of those losses in different mitigation adaptation strategies, but also do some really good fundamental basic research and understanding those responses.
All right, I think that's where we may stop it. I'll try to put this up on the website, though. Like I said, it bugs me that this isn't talked about more. Like you said, the acid levels that we're seeing in our oceans today are reflective of the CO2 in the atmosphere 50 years ago. You think about another 50 years, our oceans are going to be in a heap of trouble. And a lot of people still like to debate about whether or not it's man-made or not. The reality is it's a problem, and we need to address it, and we need to be very aware of how it's going to impact not only our ecosystem, but our food sources, and we're going to have to deal with probably the mass migration of a huge number of people globally, because a lot of people rely on the oceans for their food. So it is an important humanitarian and scientific thing that we should be looking at. I crashed again. Look at that. So I'll get off my soapbox and we can talk about the other side of this coin. And this is the reaction of water with metal oxides. And so previously we looked at sulfur dioxide and carbon dioxide. Those were all non-metal oxides. If you react a metal oxide with water, you actually get the opposite. You will form a base. So let's take a few examples of this. And so calcium oxide, if we react this with water, we're going to make a unique base. It's going to have calcium and 2 hydroxides. Why are we getting 2 hydroxides out? Think about the calcium. It's positive 2, right? So you have to have 2 hydroxide anions to bounce out the positive 2 on the calcium. All right, the next one that's fairly common is potassium oxide plus water. In this situation, you're going to be forming 2 equivalents of potassium hydroxide. But if you notice in both of these, we're creating hydroxide by mixing them together. Anytime we make hydroxide, we're making our solution more basic. These aren't typically a problem environmentally just because they're not produced on a very large scale. The bigger problem environmentally are the non-metal oxides, like I mentioned before. Does that make sense? All right. So now what we've got to do is talk about measuring the concentration of acids in water. And in order to do this, we use the pH scale. And we talked about the pH scale in lab a little bit, but I pulled this up just because I thought it was funny. This was from a health food store, and they have a pH chart. And let's take a look at the high pH. Is high pH basic or acidic? Basic. And if you look at this, they said that lemons and limes are astonishingly basic. Let's see, are there any other good ones in there? Yeah, there's a bunch of funny ones in there. And then if you go down, they've got some good ones. Let's see. My favorite is pH of most tap water is 7. That's actually not true at all. Tap water absorbs carbon dioxide from the air. And like I said, carbon dioxide makes tap water a little bit acidic, so it's not 7. My favorite is down at the bottom here. When we go down to the low pHs, we're getting way more acidic, right? Colas are apparently off the chart. I like that being pointed out. Lack of sleep is a pH of 3. Processed food is also a pH of 3. And microwave foods are a pH of 3. So what I tell people is when you go into health food stores and see any claim regarding pH, take it with a grain of salt. I've seen all these new waters coming out that are alkaline water. How many of you have seen those? Really all that means is they put baking soda into water. It doesn't mean it's more healthy. Your body is really good at regulating pH. You're not going to change the pH of your body by drinking that bottled water. So this is kind of the goofy pH scale that I like to show people because more and more you see all sorts of funky pH claims in health food stores. But we're going to do those. We're going to talk about all of this scientifically. So we've got our standard pH scale. Like in class, I said it goes from 0 to 14. And in the middle, we've got neutral. If you have absolutely pure water that's never been exposed to CO2, its pH should be approximately 7. However, as soon as you open up that water and expose it to air, it's going to start sucking CO2 out of the air and it's going to become acidic. Anything that's below pH 7 is going to be acidic. Anything above pH 7 is going to be basic. And we, in lab, went through and checked a bunch of household things. There's a bunch of them listed on here. So for example, your stomach juices, meaning gastric juices, are about a pH of 2. Cola drinks are about 2.3. They're actually on the chart. They're not off the charts. Oranges and tomatoes are acidic. Your urine is slightly acidic too. Your blood, on the other hand, is slightly basic. It's, I think most people looked that up and they said it was about 7.4. Baking soda is slightly basic. Seawater is basic, which is also why I showed that video. Is seawater is basic, but it's becoming more acidic. It's not that it is acidic, it's just becoming more acidic. So it's going to a lower pH. Household ammonia and Windex is typically pH of about 11 or 12. So you can use this as a rough guide. Yep.
Why is seawater basic?
It's a good question. So seawater is basic because of the dissolved metals in there, specifically a bunch of the carbonates. So carbonates that are dissolved in ocean water make it slightly basic. Yeah. All right, in your textbook, there's a pH table of a bunch of various household items. Most of them are pretty easy to identify. One thing I did want to point out, though, that a lot of people got wrong on their lab report was that milk-based products, a lot of people think that they're basic. They're actually slightly acidic. And that has to do with the small, short fatty acids that are present in milk. All right, so now let's get into the nitty-gritty of how we calculate pH, because right now we've just seen some sample values. And pH can be found using a log system. How many of you have seen logs in math? Hopefully everybody. I think it was in the math prereq. But it's on your calculator if you forgot. Just type in negative, hit the log button. And then in your next bracket, what you're going to do is put in your concentration of acid, meaning concentration of H+. And the other thing to remember is that concentration in chemistry is usually measured using what units? Molarity, exactly. Or moles over liters, in case you forgot. So that concentration unit is always going to be calculated in terms of molarity. The other thing, too, that some people don't know is P is actually a mathematical operator. P simply means negative log. So when you look at this, pH just means negative log of your H concentration or of your proton concentration. The same is true for Pka values. So if you've taken biology, you may have heard about Pka values. That has to do with a negative log of a Ka, which is a dissociation constant. All right, you can do the same thing with bases too. So POH, what do you think that's going to be? It's probably going to be negative log of OH. And both of these, like I said, are going to be measured in molarity, so you can calculate them pretty easily that way. Does that make sense? All right. There's also the flip that you can do. So I'm just going to erase this for the time being. So let's say we have the pH, but we want to find the concentration. We've got to do the opposite mathematical formulation, which means we need to find out the concentration of H plus would be equal to 10 to the negative pH. So you can go back and forth with these. Same thing with POH. Say concentration of your hydroxide is going to be equal to 10 to the negative POH. To factor in the negative that we had up here, you actually have to raise it to a negative power. Does that make sense? All right, there's one last thing I have to show you before we can tie this all together, and that's the relationship between pH and POH. And pH plus POH is always going to be equal to 14, which means if I give you a pH value you can figure out what the pOH is from that, and therefore you can figure out the concentration of hydroxide in solution, right? So it is a little bit tricky to think about. All right, so now let's do a few practice problems. All right. What is the concentration of acid, or H+, in lemon juice? And lemon juice has a pH of about 2.1. So I'll give you a minute to work on this, but one of the big things is making sure you're comfortable using your calculator. So we saw two different formulas for pH. So we said pH is negative log of H+, and concentration is normally shown in brackets, just as shorthand. Or you can do the opposite and say the concentration of acid can be found by 10 to the negative pH. Which of these is more appropriate to use? The right or left? The right one? I would say that's correct, right? We need to solve for concentration. We don't want to solve for pH. So let's use this one. So we know that H+, the concentration of acid, is going to be 10 to the negative 2.1, which is going to be what? Does anybody know? You said 0.0079? Okay, 0.0079, and then we need to remember our units, which are M, either capital M, or you can write it out as moles per liter. Either one is acceptable. We know that capital M is the same thing as moles per liter. Make sense? All right. Now let's try a different one. What is the pH of a 1 molar solution of HCl? Give me a thumbs up if you think you got this one. So let's try this. Like we saw before, you can find pH by taking the negative log of your acid concentration, which in this case we know is going to be negative log of 1.0. What's the answer going to be here? 0. This is something that throws people. You can get a pH of 0, and depending on the concentration, you can sometimes get a negative pH. All right, you want to see the challenge problem? Yep.
Even a negative pH, how would you display that? Because you're going between quantitative numbers 1 to 15 or 0 to 14.
Yeah, that's a good question. So the pH range is basically for normal environmental acids and bases. However, in a lab setting, you might have acids that are more concentrated.
Okay.
Yeah. All right, so this is my challenge. says prior to the Industrial Revolution, the pH of the ocean was about 8.25. Today, the pH of the ocean off our coast is about 8.14 and is projected to go to 7.80 by the year 2100. How much more acid is present today as a percent increase? And then I gave you a clue with the percent increase. What you want to do is take the current concentration of your acid, divide that by the pre-industrial concentration, subtract 1 and multiply it by 100, and that will give you the percent increase in acid. So I'll give you a minute to work on this, but check and see if you're doing the math right, and then check with your neighbor to see if you're getting the percent increase correct. Scroll up too. While you're working on that too, I'll explain this picture. So what this is showing is some of the small organisms that live in ocean water. The increase in acid isn't affecting the adults, but what's happening is it's killing the embryos before they can fully develop. So the embryo shown here is placed in a dish with acidified ocean water, and you can see its shell is forming, and then the shell is slowly degrading because the shell is made up of calcium carbonate, which is a base. If you put that base under acidic conditions, you're essentially going to dissolve that shell. This has a huge ripple effect in the ecosystem because larger animals will eat these to survive, and then larger animals will eat those animals to survive, and so on and so on. So this has a huge effect as it goes through the ecosystem. Does anybody think they got the percent increase yet? A couple people. Want to try it as a class? All right, so let's do this as a class. So the current concentration, we can find that out because we know the pH. So the current concentration, we know would be 10 to the negative pH, which would be 10 to the negative 8.14, divided by the pre-industrial concentration, which would be 10 to the negative pH, or 10 to the negative 8.25, minus 1, times 100. And what answer are you getting? 28.8. That's a pretty big increase when you're talking about environmental chemistry. Ecosystems don't like having a change of 28.8%. Especially over the span of less than 100 years. Now we get to do the projection for the future. So what I want to do now is, with this one, we looked at today's pH. Let's do the projected pH of 7.8 that we're expecting by 2100. Pre-industrial, yeah. What's that? Yeah. So I said that the projected pH by 2100 is supposed to be 7.8. Let's try this again with the calculator. We can plug it in pretty similarly. Say 10 to the negative 7.80 divided by 10 to the negative 8.25 minus 1 times 100. Anybody get an answer for this? What were you getting? 182? And if you are struggling with this, one thing you can do is solve your numerator separately, solve your denominator separately, and divide those two answers. Sometimes that prevents calculator errors from occurring. But the thing that hit me, I mean, I'm not going to lie, I have my PhD and I didn't do this math problem until recently. You think about this, right? Our oceans are going to get almost twice as much acid in them in the next 60 years or 80 years. That's pretty shocking when you think about it. And it goes back to that video saying all of the acid we're detecting off the coast today is actually from CO2 emitted 50 plus years ago. We've done nothing but exponentially increase the amount of CO2 we're emitting, which means we're going to have this huge spike in ocean acidification. So something to think about. That's where we're going to stop today. I would say if you have a chance to ever take an environmental science or ecology class, definitely jump on that opportunity. They are fascinating courses.